All right, hello everyone. So in this talk, I'm going to talk about puckering versus buckling phenomena in 2D materials. This work is inspired by some recent experimental observations which report that there are materials which exhibit a new emergent phase in 2D limit, and that is not intuitive if you look at the bulk structure of the same material. So let's learn more about these emergent 2D phases. Before I go further, I would like to first define what do I mean by buckling and puckering words. So I'm sure all of you are familiar with graphene, and as Cyrus talked about boron nitride monolayer, which has honeycomb structure with two sublattice. This is the side view, and now imagine distorting this atom out of the plane. So if you shift it upwards while maintaining the honeycomb structure, then you get a buckled honeycomb monolayer. And there are materials which show this particular phase in 2D limit. Now to understand puckering, I would like you to imagine a 2D square lattice and think of two atomic planes stacked right on top of each other, and this is a high symmetric configuration. If you look from side, this would be a very high energetic configurations. So to minimize the energy, these atoms, they try to distort, and as a result you get this kind of distorted phase. And in literature people call that puckered monoclinic phase, and this phenomena is known as puckering. And here are some examples of materials which show puckering in monolayer form. In this talk I will be focusing on group 5 monolayers which show both buckering and puckering phenomena in 2D. This is the valence configuration of group 5 monolayers, and these are the members of this family. In this talk, I have decided to choose bismuth as a prototype, so I will be talking more about bismuth element, but the results are valid for any of these members, as we will discuss later. You might be aware of that phosphorine was one of the first 2D material that was experimentally synthesized right after graphene, and this was one of the most popular discoveries of year 2014. And since then, a lot of work has been done in this direction, and now people have managed to synthesize monolayers of these elements in the elemental form as well as binary form of group 5 elements. It turns out that all the monolayers from this family, they tend to have a puckered phase, as we discussed before, and this is not obvious because if we take bismuth for an example, we all know that bismuth crystallizes in rhombohedral phase, right? This is the structure in space group R3 bar M. And now if you think of exfoliating one monolayer from the bulk structure, you would naturally expect it to have buckled honeycomb structure, right? And indeed this has been synthesized, so people have grown bismuth thin films where bismuth atoms, they occupy tend to have this buckled honeycomb ordering. And here are some references for that, and it has its own interesting physics, like it's a good thermoelectric and 2D topological insulating phase has been reported in this material. However, there are some other experimental observations which suggest that below 4 monolayer thickness, bismuth tends to have puckered phase, which is something like this. And now this is not one experimental report, there have been like several other reports from different groups, and they have reported this phase as the ground state of bismuth. Now one question is that, are there some more phases of bismuth in 2D other than the buckled one and puckered structure? Now to answer that question, I performed a structural search calculation in 2D using minima hopping method. So this method employs an algorithm which couples DFT with molecular dynamic simulation, and it tries to find local minima on multidimensional potential energy landscape. Now to restrict the structural search in 2D, I added confinement potential, so that restricts the motion of these atoms within a predefined thickness, and then I carried out the structural search, and as a result I found bunch of new structures as well as the reported phases of bismuth. If you look here, from these calculations I found that puckered phase is indeed the lower, the ground state lowest energy structure, and buckled one is the first metastable, and there are other metastable phases with distinct electronic properties, and that has been reported in this work. Now, so what we know so far about bismuth monolayer and other group 5 monolayers. So we know that bismuth as well as other elements of this family, they have ground state phase which is puckered, and the buckled one is the first metastable, and there are other high symmetry like higher energy structures. Interestingly, in a recent work, this group, they have experimentally synthesized a flat honeycomb monolayer of bismuth on top of silicon carbide substrate. This is pretty interesting because this is a very high energy structure, and this has very unique electronic properties because the band gap is about 0.8 electron volt. So, and this is a candidate, because of large band gap, this is a candidate for realization of high temperature quantum spin Hall phase. So, and another good thing about this discovery is that now we know that since people can stabilize this phase, so all the intermediate phases, they are within the reach of experimental synthesis. So, it's worth exploring the intermediate phases. Now, so far in literature, people have studied this phase, this structure and the puckered phase, but all independently. What we do not know what is the connection, what relates these phases to each other. We do not know what causes buckling or what causes puckering in these 2D monolayers. So, these are the questions that I am going to address in this talk, at least in terms of phonon mode distortion. So, this is our approach to address these questions. So, we start with a high symmetry parent phase of bismuth, which is flat honeycomb monolayer in space group 191, just like graphene, and then we consider all the allowed out of plane distortions, because any out of plane distortion from this high symmetry phase is expected to lower the energy of the monolayer. And we use IsoDistort software together with Pisotropy package, which was developed by John, and it's available at this link, to figure out all the allowed out of plane mode distortion modes. And after that, we relax all the distorted structures freely using DFT, and then we compute the total energy. Here are some other computational details. So, this is the calculated phonon spectrum of bismuth monolayer. So, there are 2 atoms per unit cell. So, in total there are 6 phonon branches. Here I have highlighted out of plane modes in red color. Now, let us start looking from the simplest modes. So, the simplest one is this ZO mode, which is a transverse optical mode, and it corresponds to out of plane vibration of these 2 atoms. One goes up and another goes down, and this is gamma 3 mode. So, if we distort the structure along this particular mode and we compute the energy profile, this is what we get. So, when the distortion amplitude is small, we are within a local minima, and that makes sense because this is a stable phonon mode, right? It has positive frequency. But we see that when we hit beyond a critical amplitude, the structure migrates to a much lower energy phase, and that is the buckled hexagonal structure, and that belongs to space group 164. So, now we understand a gamma 3 plus mode causes buckling in the flat monolayer structure. Now, let us look at out of plane M modes. For instance, this is M2 minus mode. So, here I just tried to make an schematic of this particular phonon mode. Since it is a M point phonon mode, so it causes cell doubling. So, now we have 4 atoms per unit cell. Here red dots, they show atoms which are coming out of the plane, and the blue dots, they represent atoms, they are vibrating down the plane. As you can see that 2 atoms, they vibrate upwards and 2 they go down. If you look from the side view, you see this kind of structure. This is armchair direction, 2 are up, 2 goes down, and then again 2 go up, and so on and so forth. This looks like puckered structure, but this is not the exactly puckered phase that we are looking forward. Now, we look at another out of plane M phonon mode, which is M3 plus mode. Now, this causes out of plane vibration of this zigzag direction. So, all these atoms, they vibrate upwards up the plane, and these this chain that vibrates down the plane. Again, this is not the exact puckered phase that we are looking for, or that has been reported in literature. So, what causes the exact puckered phase? So, we find that if we combine these 2 modes, if we make a linear combination of M2 minus and M3 plus mode, then we get the exact puckered monolayer structure that has been reported, and it has in plane ferroelectric polarization. It belongs to space group, polar space group number 31. Now, so here is a table. I do not expect you to go through this table. This has been provided in the abstract book. So, here we have listed all the out of plane distortion modes that we have considered in our study. So, this is we have gamma k point and M high symmetry points, as well as superposition of different distortions. So, here we list the 3D space group of the distorted structure, the layer space group, and our label, and how many atoms we have in the primitive cell. Then we list the energy gained by each distortion. calculated without spin orbit coupling as well as with spin orbit coupling. So if you see the parent phase has everything is listed with respect to the parent phase. So if we distort gamma 3 mode in the parent structure, we gain about 415 milli-electron volt per atom energy, and if we distort a linear combination of these two modes, then we gain about 420 milli-electron volt per atom energy. Here is an schematic of the same information. So this is the parent structure, and all the K modes, they reduce the energy little bit, maximum is almost 200 milli-electron volt per atom, and all the M point distortion, they bring energy further down, and the buckled phase that we get from the gamma 3 plus distortion, that comes around here, but the lowest ground state structure that we get when we make a superposition of these two modes. These two blue lines, since these phonons are stable in the parent phase, so one has to overcome an energy barrier to get to these phases, but these modes, they are unstable in the parent phase, so you can just slide downhill, there is no energy barrier. And this one, which is a superposition of two modes, there is a very tiny energy barrier that one has to overcome. So that was the story about bismuth monolayer, and we find that the same story is valid for other members of this family, like in group 5 elements. We find that the puckered is the ground state and buckled is one of the metastable, and there are other high energy structures. Now you might wonder, is it useful or not? So what I am asking that, like is puckering good for us or bad? Like had we had buckled honeycomb lattice, would it be better, which is just like the bulk structure? It turns out we find that it is actually great, at least in context of this workshop, because there are proposals that one can realize ferroelectricity as well as anti-ferroelectricity in these elemental monolayers, and there are proposals for piezoelectricity, negative Poisson's ratio, and large hole mobility, which is due to very anisotropic band structure in these materials. Here I am going to talk about just ferroelectricity. How does ferroelectricity come in this picture? So because of this puckered distortion, you see one atom moves out of the plane, like outwards, and due to this puckering there is a charge redistribution, and there is a charge accumulation at this site and charge depletion here. As a result, you have negative charge on the atoms which are distorted outwards and positive charge which are inwards. So as a result, you can see there is a kind of dipole formation from this to this direction, and that is consistent everywhere. And as a result, you are like we get a net ferroelectric polarization which is in the in-plane direction along B lattice vector. And this in-plane polarization can be flipped, and from this reference they have reported the energy barrier that one needs that is required to overcome this polarization switching, and it is listed for these different elements. They have also reported the transition temperature obtained from Monte Carlo simulations. As you can see, the transition temperature is pretty large, it is well above the room temperature, and here are the values of the ferroelectric polarization. So for comparison, I have listed numbers for tin telluride, and as you can see there is a fair competition between these systems and tin telluride, and these are the experimental numbers. Now while you do that comparison, you have to acknowledge the fact that these are elemental systems, and having such large ferroelectric polarization in elemental monolayers is pretty amazing, right? Now we think of what if we make it binary. So here we have these two atoms are bismuth. What if we replace one by antimony or some other group 5 elements? So now we further consider binaries of the same group 5 monolayer. Now we have one bismuth, another one is antimony. What is the advantage here? That we have naturally we have broken the inversion symmetry. So all the distorted phases, it is more likely we are going to discover new 2D ferroelectric materials because of the broken in centrosymmetry. Now the space group is different and 2D layer group is different too. Now the notation of the phonon modes will be very different than we have discussed earlier. Here is the computed phonons of bismuth antimony monolayer. These are out of plane modes highlighted in red color. Now if we pay attention to this transverse optical mode, which is gamma 3 mode, it causes buckling in this flat bismuth antimony monolayer. And if we pay attention to M point phonon mode, this is M3 mode, we find that this causes puckering in this monolayer. And in this phase there is an in-plane ferroelectric polarization along B lattice vector. You can notice that here too, like along from this antimony and this is bismuth atom, along this direction there is in-plane ferroelectricity. So in summary, we find that buckling is caused by a gamma 3 plus mode in elemental monolayers, and puckering occurs because of a superposition of these two out of plane M modes. In case of binary monolayers, we have gamma 3 mode that gives rise to buckling and M3 mode that causes puckering. Why these materials are important? Well, because as I discussed before, because of the possibility to realize ferroelectric polarization, and also we find that we discovered some new stable 2D monolayers. In bismuth, especially because of large spin orbit coupling, there is a fair chance of discovering new topological phases. We also think that there might be good thermoelectrics and piezoelectrics in properties that can be realized in these materials. In future, we plan to extend this study and study the distortion modes in other 2D materials. Right now, we are focusing on group 5 elements, all the elemental as well as binary monolayers. And our plan is to get the data tabulated in form of a database, so one can choose the elements and see what is the high symmetry parent phase and which phonon distortion will give rise to how much energy. If that distorted structure is stable, then what are its properties? So that is our future goal. With that, I would like to thank you for your attention. Yeah.
Very nice talk. Thank you.
Thank you.
Maybe you mentioned it, but what is the band gap of the different polytypes?
So, all are semiconducting. In case of bismuth, gap is smaller. It's about 0.5 electron volt. But as we go to up in the periodic table, like phosphorine, that has band gap of about 1.8 to 2 electron volt. Yeah.
More questions?
Yep.
Oh.
So, very nice talk.
Thank you.
I get confused. For the mode decomposition, you use ISO distort, right? For
Right.
3D space groups.
Mm-hmm.
So, in this case, then how do you make the mode decomposition for layered group?
Well, because of the symmetry, we can figure out what mirror operations we have, how many symmetry operations you have. Then we use Bilbao crystallographic server, and there you can figure out what is the corresponding layer group. If you have a bulk material and vacuum is along 0, 0, 1 direction, then what would be the possible layer group for that particular crystal structure? So yeah, that is implemented on Bilbao crystallographic server.
Okay, thanks.
More questions? I have one.
Yeah.
In your table, the one that we were not supposed to pay attention to,
Okay.
you can show it again.
Sure.
You had you had many polymorphs, and you were giving the energy with and without including spin orbit coupling in the calculation, right?
Mm-hmm.
So spin orbit coupling raises the energy of all the polymorphs except one. Have you thought about that one? Is it special?
Yeah, I know what you are talking about. Yeah, but I think it will be a little unfair to compare the energies with respect, because spin orbit coupling changes energies of all the phases, and it depends whether you have invergent symmetry or you do not have invergent symmetry. The role of spin orbit coupling will be different, right? And it not only changes the structure energy of these distorted, it changes the energy of the parent phase too, right? And everything is listed with respect to the energy of the parent phase. So yeah, I think it won't be.
Maybe you didn't get my question. There is one particular polymorph that gets more stable with respect to the parent phase.
I know what you are talking. I think this one is that one,
yeah.
Right? It so here it's -41 and it goes to negative. It increases basically.
Yeah.
I do not have just one answer to you. I give you and you will be satisfied. I really do not know, but yeah, it will be
just curious.
Yeah, I think it depends more on the symmetry and details of the structural.
Nothing very important.
Atomic arrangement.
So let's thank the speaker again.
Thank you.